Hello Stats AP friends. Today you're going to learn about probability, and that's chapters 13 and 14 in your textbook. Here are some definitions that you should know, so please make sure you go over them and understand them. Here are some probability rules and formulas that you also definitely need to know, so please make sure you review those, memorize them, and understand them. Today we're just going to go through the examples and apply those definitions and formulas. So here's our first example, number 1. Find the sample space and determine if the outcomes are equally likely. So if you look at your definitions, a sample space is the set of all possible outcomes for an event. So for example, if letter A, if I were to roll a die, all of the possible outcomes for this event would be 1, 2, 3, 4, 5, 6, assuming I'm rolling a standard die. And those outcomes should be equally likely, assuming we have a fair die. So we're going to put yes, equally likely for a fair die. So that's a sample space for letter A. Letter B. Let's do a sample space for the tossing 2 coins. So again, we need to list all of the possible outcomes if you were to toss 2 coins. So if I toss 2 coins, one possible outcome would be tails, tails. Another one would be heads, heads for both of my coins. Another one could be tails, heads. And there's actually one more outcome, which would be the other way around. Like the first coin could have been the head, and the second coin could have been the tail. So those are 2 separate events. And now you have 4 events, and all of those are also equally likely if you have a fair coin, because the chances of tails, tails would be 1/2 times 1/2, so 1/4. This is also 1/4, 1/4, 1/4, and they all add up to 1. So we're going to put yes, equally likely for a fair coin. So now we'll do one more sample space, and this time we're tossing 4 coins. However, here we're going to write down the number of heads. So our sample space should be the number of heads. So again, if I were to toss 4 coins, the possible number of heads could be 0. I could have no heads at all. Or 1, 2, 3, 4. And now we need to determine if those events are equally likely. And the answer is going to be no, they're not equally likely. Not equally likely. Here's why. Likely. Because, so let's start with the first event here, the first outcome. So if the number of heads is 0, there's only one possible way for that to happen. And that's if your 4 coins were all tails. Tail, 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 tail. So that's the only one possible way to have 0 heads. However, when we get to the 1 head, that one has multiple possibilities. For example, you could have the head was the first coin, and then the rest were tails. Or it could have been the head was the second coin, the other ones were tails. Or it could have been that the head was the third coin. Or finally, the head could have been the last coin that you flipped. So therefore, having 1 head has 4 times as many choices as options, or I guess possibilities, as the first one here. So you can continue going the same way for the rest, but we're just going to say they're not equally likely because there's more ways to get 1 head compared to the 0 heads. Now for number 2, it's still talking about sample spaces. Which of the following are legitimate sample spaces? So for the legitimate sample spaces, your probabilities have to add up to 1. Yeah, that was one of the rules that you need to know. The probabilities have to add up to 1. Probabilities should always be between 0 and 1, so it can't be negative and it can't be more than 1. So let's do number 2, letter A. Here is your spinning a spinner. And you have some probabilities here, 1/2, 1/3, 1/4. That's not a legitimate sample space. No, because those probabilities add up to more than 1. 1/2 plus 1/3 plus 1/4, that adds up to more than 1. Probabilities add to more than 1. And for a legitimate sample space, the probabilities have to add up to exactly 1 for your whole sample space. Number 2, 2 coins are tossed. Here's some probabilities. Okay, automatically, definitely not legitimate because you can't have a negative 1/4 there. You can't have a negative probability. So no, because we can't have a negative probability. Plus, they don't even add up to 1, so that's just wrong. So that's some information you need to know about sample spaces. Now, the next example that we'll be doing is actually finding probabilities of events. So our first event here on number 3 says that a die is rolled. So again, assuming we have just a standard fair die, the numbers 1, 2, 3, 4, 5, and 6. Now let's find these probabilities here. It says A, the number is even. So I do definitely need you to write what's called like notation. So what we're going to do for our notation is you put P for probability, parentheses, and now here you put the event you're looking for. You're looking for the number is even, so we're just going to call it even. Okay, so now you look at all your outcomes here and you figure out how many of those are even. So obviously 2, 4, 6 are even numbers, so that's 3 out of the 6 outcomes are even. So therefore your probability of an even number would be 1/2. You can leave it as a fraction or a decimal. Either one's correct. Letter B says find the probability that the number is prime. So if I were, make sure you put P for probability, parentheses, prime. So again, if I were to roll a die, what are the chances that it is prime? These are the outcomes. The prime numbers here would be 2, 3, and 5. So again, we have 3 out of the 6 numbers there are prime, which are 2, 3, and 5. So again, that's the probability of a half. Probability that the number is even and prime. So even and prime. So I'm abbreviating even with E, prime with P, and then this is the and symbol, the intersection. So you look at your numbers and you figure out which ones are both even and prime. So remember I told you the prime numbers were 2, 3, and 5. So now look at those and see which ones are both even and prime. It looks like only 2 is the only number that's both even and prime. So that's just one option out of the 6. So that is the probability of a number being both even and prime. It was only the number 2, so that's 1 out of 6 outcomes. So that's for letter C. And then the last one, the number is even or prime. So the probability the number is even or, we use the union symbol for the or because it's a union, even or prime. Okay, so for this, for the or event, you have to use the general addition rule. So if you go back to those rules that you need to know and memorize, here's the general addition rule. Every time you're trying to find the union of A or B, remember this is an or, you need to take the probability of A plus the probability of B and then subtract the intersection. This is an and, which is an intersection. Subtract A and B. So that's what we're going to do. The probability of even or prime, I'm going to use a formula. It's going to be the probability of even plus the probability of prime minus the intersection of even and prime. So we already have all that information because we already did the probability of even was a half, the probability of prime was also a half, and we just found the intersection of even and prime to be 1/6, so we subtract that. Use your calculators, and that would be 5 out of 6. So 5 out of these 6 numbers are both even or prime. So all of them except for 1. And that's how you do some probabilities with rolling a die. It helps if you write down your sample space. So for number 4, one card is drawn from a standard deck of cards. So you do need to be familiar with the standard deck of cards. So we're not going to write the whole sample space, but here's some information you need to know about a standard deck of cards. Definitely make sure you know this. And if you're not sure, go play with the deck of cards. But In a standard deck of cards, there's 52 cards total. There are what's called 4 suits. And the suits are clubs. The suits are clubs, spades, hearts, and diamonds. So those are the 4 suits. Each of those 4 suits has 13 cards. So 13, 13, 13. And that's why there's a total of 52 cards. You do need to know that the clubs and the spades, those are black cards. So the color of those are black. Black. Hearts and diamonds are red cards, because you will be asked questions like black and red. Then you also need to know that out of those 13 cards in each suit, 3 of them are called face cards. 3 face cards, because when you look at the cards have like a little face, like a person's face on it, and the face cards for each of those suits are the jacks, queens, and kings. So the jacks, queens, and kings, those have little faces, so they're called face cards. So all of these suits have 3 face cards. The rest of the cards, so the other 10 cards for those suits, are an ace, which is like the number 1, and then 2, 3, all the way to 10. So that's where the 13 cards come from, and you need to be familiar with them. So let's start, I guess let's use that information to start doing example 4. Okay, I am drawing one card. It says letter A. What is the probability that the card is a king? Make sure you use notation, and then you can abbreviate. I'm just going to put probability of K. The probability that the card is a king, like I told you, there's one king for each of those suits. So that's going to be 4 kings out of a total of 52 cards. And if I reduce that fraction, it's 1/13. You can leave it as a reduced fraction or as a decimal if you want to calculate that. Letter B, what is the probability that the card is an ace? Again, each of those suits have 1 ace. So there's going to be 4 aces out of the whole total. 4 aces out of 52. So that's 1/13 again. What is the probability that a card is a heart? Probability of a heart. I told you that the deck has 13 hearts altogether. So that's 13 cards out of 52 are hearts. And that reduces to 1/4. Okay, now we start doing the, let's see, the card is an ace and a king. So probability of ace and a king. So if you're drawing one card, how many of them are going to be both an ace and a king? Okay, for that, it's going to be 0, because being an ace and being a king are what's called disjoint events. Disjoint / mutually exclusive. That's one of your definitions that you need to be familiar with. Mutually exclusive. So if you look at your definitions, disjoint events / mutually exclusive, those are the same term. It's when events have no outcomes in common. So here's like these are the cards that are aces, and then here are the cards that are kings. They don't intersect, so that a card can't be both an ace and a king. So they're called disjoint events. So the probability of A and B would be 0 for disjoint events, and that's the scenario here. If you draw just one card, it's not possible for it to be both an ace and a king. However, let's look at E. The card is an ace and a heart. Like, that will be possible. Ace and a heart. So if you look at your standard deck of cards, it's possible to be a heart and an ace, because there actually is an ace of hearts. So basically for that one, we're going to put 1 out of 52, because there is one card in the whole deck that's both an ace and a heart, and it's the ace of hearts. Ace of hearts. So therefore, the probability of A and heart would be 1 out of 52. Keep going. Letter F, what is the probability that the card is an ace or a king? So the probability ace or king. Again, you have to use the formula for the union of 2 events, which is the probability of A plus the probability of king minus the intersection. Don't forget to subtract the intersection. So here, the probability of an ace was 1 out of 13. The probability of a king was also 1 out of 13. And then remember, we just talked about the probability of ace and a king was not possible, so that's 0. Just write down 0 anyway. So my answer for ace or king should be 2 out of 13. And we can leave it as a fraction or a decimal. And then finally, what's the probability that the card is ace or heart? Same thing, ace or heart. You have to use the general formula for union. So the probability of A plus the probability of H minus the intersection. This is the most common mistake. Students forget to subtract the intersection. So ace was still 1 out of 13. Hearts was 13 out of 52, which is 1/4. Okay, that's fine, 1/4. And then we do subtract the intersection because I just said there was an intersection of ace and hearts, which was 1 out of 52. So when you do all of that, it comes out to be 4 over 13. And that's an example with a deck of cards, so please make sure you're familiar with them. And now for the rest of these here. Example 5, E and F are mutually exclusive events. So remember, that means that they don't have any outcomes in common. If the probability of E is 0.2 and the probability of F is 0.1, find the following. Find the probability of E or F. Again, there's that formula that you need to know. That equals to the probability of E plus the probability of F minus the intersection of E and F. So the probability of E is 0.2. The probability of F is 0.1. The intersection of E and F, since they're mutually exclusive, is going to be 0. So my final answer would just be 0.3. And that gives us the answer for letter B. Find the probability of E and F. Like I just said it, they are mutually exclusive. So it would be 0 because mutually exclusive. Slash disjoint. So that's how you would do something like number 5. And now number 6 says, given that the probability of having a blue M&M is 0.38, a red M&M is 0.36, and then I guess we don't know the rest of the colors, but that's fine. If you select 2 M&Ms at random, find the following. The probability that both are blue. Make sure you write notation. So if I were to draw 2 M&Ms, you just do one at a time. The first M&M, the chances of it being blue would be 0.38. The second M&M, chances of being blue is still 0.38 because for here we don't have a specific sample size, so we assume we have like infinite M&Ms, so the probability will remain the same. And if you do 0.38 square, that's going to give you 0.144. You can round to 3 decimal places, 4, it doesn't matter, just show your work. And that's letter A. Now let's do the probability that neither is red. So again, if I draw an M&M, the chances of it not being red would be the complement of 0.36. So that would be 0.64 for the first M&M, and again 0.64 for the second M&M. So that's not red and not red. And maybe multiply those together, that gives me 0.4096. And finally, this probability of at least one, again, that's another formula that you need to know. The probability of at least one success is always equal to 1 minus the probability of no successes. So, the probability of at least one red. At least one red would equal to 1 minus none red. Or neither is red, I guess. So that would be 1 minus neither is red. We just did that on part B, so that would be 0.496. So if I subtract 1 minus that, it's going to give me 0.5904. And that's how you do something like number 6. And then finally, our last example is number 7. A bag contains 5 red marbles, 4 black marbles, and 3 white marbles. If you select 2 marbles with that replacement. So this one, our probabilities are going to change because you have a set number in your sample. So there's only 12 marbles total. and then you're not replacing them, so the probabilities will change. So the question says, what is the probability of getting at least one black marble? So the probability of at least one black marble will be 1 minus 1 minus the probability of none are black. So therefore we're going to do 1 minus, so here are the chances of not having a black marble the first time. So when you go into the bag, there's going to be, like I said, there's going to be 12 marbles. The chances of them not being black is going to be the 5 red plus 3 white, so 8. 8 out of 12 marbles are not black. So that's my first probability. However, for my second probability, since you're not replacing the marble, for my second probability, there's no longer 12 marbles in the bag. Now there's only 11 because we didn't replace it. And if the first marble was black, because I needed or not black, then that means there's only going to be 7 not black marbles left in the bag. And so you would do 7 out of 11. And now if you simplify all that out, it comes out to be 19 over 33, which you can leave it like that, or you can change it to a decimal if you prefer. Around 3 or 4 decimal places, it doesn't matter. So now you need to practice your probability with the homework.